Now for question 4, you have a child that moves down a long slide as shown in the figure below. The child moves from rest at the top end X of the slide. An average resistive force of 76 Newton opposes the motion of the child as they move to the lower end Y of the slide. The kinetic energy of the child at Y is 300 joules. The decrease in gravitational potential energy of the child as it moves from X to Y is 3,200 joules. From here, determine the ratio of the kinetic energy of the child at Y when resistive force is 76 newtons to the kinetic energy of the child at Y if there is no resistive force. Now you read back the question. When they told you that the kinetic energy of the child at Y is 300 joules, this is the one with resistive force. This is the kinetic energy of the child with resistive force. So what you really need to find here is the kinetic energy of the child at Y if there is no resistive force. Now just consider this. If the child is moving from X to Y in this direction here, according to conservation of energy, it will be decrease in GPE equals to the increase in KE plus work done against friction. Now your GPE is decreasing because there's a decrease in height, and then because your child started from rest here, as stated by the question, this one would be having a KE at X of 0. So as the child moves down, that child would eventually have a certain velocity V. So there is an unknown kinetic energy Y here, which we want to find out. Okay, so there's an increase in KE here because you started from 0 and then eventually you attain some sort of speed. So your kinetic energy here is increasing. Now, as for the work done against friction, you are specifically considering the case where there's no resistive force. So this one will not be considered because it's really just 0. So what you end up with is really just the decrease in GPE equals to the increase in KE. Okay, so the question did mention to you what was the decrease in GPE. That one would have been 3,200 joules. So you have 3,200 here. And as for the change in KE, it will actually be the KE at Y minus the KE at X. You take the higher value minus the lower value. So if you try to find out what is your KE at Y now, you will actually get 3,200 equals to KEY minus 0, because the K at X is actually 0 in the first place. So therefore, your KE at Y is actually going to be 3,200 joules. So now if you want to find out what is your ratio between the two KEs with resistive force and without resistive force, it's really just going to be 300 divided by 3,200, giving you 0.0938. Okay, so let me just write out the answer here, 0.0938. Let's check whether the answer is correct. For 4, yes, it's 0.094. It is the correct answer if rounded out to 2SF. Then if you move on to part B wants you to use your answer in A, the one that you just did, to find out the ratio of the speed of the child at Y when the resistive force is 76 Newton to the speed of the child at Y if there's no resistive force. Okay, you're still finding the ratio with resistive force to without resistive force, but here they want the speed. So since they ask you to relate to the question above, you are talking about KE here. KE is related to speed by this equation. Is equals to half mv squared. Now this equation would apply to the motion of the child with or without air resistance. But for both cases, you will notice that the mass is constant. So what I can further say from here would be this. Mass being constant would mean that KE is directly proportional to the velocity square. So that V2 square to V1 square is equals to KE2 to KE1. Okay, Let's just consider the case V2 here is as the one with resistive force. Okay, and case V1 here below is the one without resistive force. Okay, so now if we want to find out the ratio of the speeds with resistive force to without resistive force, it will be V2 to V1 equals to square root of KE2 to KE1. Okay, the ratio of the KE with resistive force to without resistive force has actually been found in part A above, so we can use the answer directly. So what we end up with now would be something like this. It will be 0.0938 square root of that answer. We will get the answer as 0.306. Okay, so let's just check whether that will be our answer here. Yes, it is going to be the answer. It will be 0.31 if rounded up to 2SF. All right. Okay, then we move on to part C. So let me just clear all the writings here. Now for part C, calculate the length of the slide from X to Y. Now recall that earlier you had some sort of inclined plane, and then the child was moving from position X here to position Y here. Okay, you want to find out the length between X and Y. Let's call this distance S. All right. And as the child was moving from position X to position Y, that child was actually experiencing some sort of resistive force. Let's call this force FF. Okay. So there's work done against friction to consider here. If you were to consider conservation of energy, it will be decrease in GP of the child equals to the increase in KE plus work done against friction. Okay, so work done against friction can be further expanded to become the frictional force times the distance moved. Because originally when you're talking about work done, is actually force times distance moved in the direction of the force. You apply it for work done against friction. So if I want to write out the working now, it will be something like this. Decrease in GPE equals to the increase in KE plus work done against friction. Expand it out, I'll get decrease in GP equals to increase in KE plus frictional force times distance moved. Okay, so all that's left now is to sub in the relevant values. The decrease in GP was already mentioned to you as 3,200 joules from the question above here. So this one is 3,200. And then as for the increase in KE, just now we know that the child was moving from rest, and then as he reached point Y, your kinetic energy is 300 joules. So here just now we say that KE at X is 0, but KE at Y is 300 joules. So the increase in KE here is really just 300 joules. Okay, and when you're talking about the frictional force here was mentioned to be 76 Newton somewhere. Let me just find out where it is. Yes, it's over here. The question mentioned that the average resistive force of 76 Newton opposes the motion of the child. So this one would be 76 times your distance moved. So in our case, the distance moved would likely be 3,200 minus 300 divided by 76, giving us the answer as 38.2 meter. Okay, let's just check whether this answer is correct. Yes, it is correct. It is 38 meter. So now let's move on to part D. In the next part, at NY of the slide, the child is brought to rest by a board as shown in the figure below. A spring connects the board to a fixed point. This spring obeys Hooke's law and has a spring constant of 63 Newton per meter. The child hits the board so that it moves to the right and compresses the spring. The speed of the child becomes 0 when the elastic potential energy of the spring has increased to its maximum value of 140 joules. From here, calculate the maximum compression of the spring. Okay, When you want to find out the maximum compression of the spring, you need to know what is the maximum elastic potential energy of the spring. It's already stated in your question right above here where they told you it has a maximum value of 140 joules. So when it comes to EPE, there are two equations to use. It's either half Fx or half Kx squared. Now you cannot use the first equation because you do not know what is the force at maximum compression. The question never stated that. But what you do know from the question is the spring constant. They've already told you that here. And you also already know what is the elastic potential energy at maximum compression. So from here, you can find out what is going to be your compression. So you will use the second equation. So if you use it right over here, you should rightly get EPE equals to half Kx squared. You will get a maximum value of 140 joules equals to half times 63 times x squared, eventually giving you an answer of 140 times 2 divided by 63 square root of that. You get your answer as 2.11 meter. So let's just check whether our answer is correct. Yes, it will give you 2.1 meter at 2SF. All right. In part 2, you want to calculate the percentage efficiency of the transfer of the kinetic energy of the child to the elastic potential energy of the spring. Let's consider the energies that are involved here. It was mentioned at the beginning of the question that at NY of the slide, the child is brought to rest by a board. So if you look at point Y here, the child actually had a kinetic energy of 300 joules. The child actually kept moving after that until he hits a board that is connected to a spring. So when the child was hitting the board, his kinetic energy should rightly be the kinetic energy at Y. It was 300 joules. So the child kept moving. He pushes against the board, compressing the spring until he eventually comes to rest. So your KE here is going to be 0. Now, as the child was compressing the spring, there will be an increase in EPE because there's increase in compression. The change in your EPE here was from 0 to a maximum value of 140 joules. So your change in EPE here is actually 140 joules. Okay. Now, you also have to consider that when the child was moving towards the right, compressing the spring, there is also frictional force opposing the motion of the child. If you consider the conservation of energy for this situation now, you will actually say that the decrease in your KE is equal to the increase in your EPE plus the work done against friction. Okay. So right now, what is your change in KE? Your change in KE is between 300 joules to 0 joules. It's going to be 300 here. Your increase in EPE is going to be 140 joules. And your work done against friction, it will just be the difference between 300 and 140, giving you 160 joules. Okay. Now, if you look back at what the question wanted, they want the percentage efficiency of the transfer of kinetic energy of the child to the elastic potential energy of the spring. From the diagram above, you can see that initially the kinetic energy is 300 joules, but not all of it was converted to elastic potential energy at the end. Only a fraction of it was converted to elastic potential energy. So in your case, the percentage efficiency here really refers to the fraction of kinetic energy that was converted into elastic potential energy. So now over here, if you had wanted to find out what is the efficiency, it will be the elastic potential energy that you had at the end divided by your kinetic energy that you had at the beginning times 100%. So it will be 140 divided by 300 times 100%, giving you an answer of 46.7%. So let's check whether this answer is correct. Yes, it is 47% when rounded up to 2SF again. Then let's move on to the last question. For the last part of the question in part 3 here, The maximum compression of the spring is x0. On the figure below, sketch a graph to show the variation of the elastic potential energy of the spring with its compression x from 0 to x0. Numerical values are not required. You want to plot a graph of EPE versus compression here. When it comes to EPE, there were two equations that we usually use. The first one being EPE equals to half Fx. If you were to compare this with the equation of a straight line, y equals to mx plus c, you would have probably said that the y-axis would be equals to your EPE, the x-axis will be equals to your compression, and then lastly, your gradient would be equals to half f. So that if you were to plot a graph of, say, EPE versus compression right now, you ought to get a straight line graph that passes through origin. But this way of doing the question is wrong, because you need to realize that when you are using the equation y equals to mx plus c, y and x are variables. They are supposed to vary, but m itself should have been constant. So now if you look at the equation for EPE, you cannot actually say that f is constant. It's actually not constant here. Because if you're talking about a spring obeys Hooke's law. So the equation that relates to Hooke's law is F equals to Kx. Your spring constant is a constant, so force is directly proportional to X. From here, you can actually see that if X increases, F increases. Applying it to your question, this could mean that when your compression increases, your force inside the spring also increases. So here, you cannot really say that your force is constant. It's actually not constant. So therefore, this equation cannot be directly compared to the equation of a straight line. You would not use this method. But you can use it for another different equation, which is EPE equals to half kx squared. Now, in our case, we already know that the spring constant is a constant in itself. It will not change. So now, if we were to compare this with the equation of a straight line where y equals to mx plus c, you could rightly say that the y-axis is my EPE, the x-axis is my compression squared, and then lastly, my gradient is actually half k, okay? So here, if you then want to plot out a graph of, say, EPE versus compression square, you will get a straight line graph that passes through origin. But the question here doesn't want you to plot compression square. They want you to just plot it against compression, okay? So you can actually do so if you change this graph into this form. Let me just draw it out for you. If you were to plot a graph of EPE versus compression right now, this is the graph shape that you expect to see. It's going to be a curve with increasing gradient like this. Okay, you've learned about this in maths before. In maths, we told you that if y is proportional to x, then your graph will just be a straight line graph through the origin if y is plotted against x. And then if you have y is proportional to x squared, a graph of y versus x squared will again be a straight line graph through the origin. But if you were to just plot a graph of, say, y versus x only, you will actually get a curve with increasing gradient. So you're applying the same thing over here. So your answer would be something like this, a curve with increasing gradient. You can check it with the marking scheme. The marking scheme says that it must be a curved line from the origin and the gradient of the line increases. So this is for question 4.